Anyway, we're looking very forward to your talk on oil fuel tank measuring technologies. And what we're really interested in is how you got there and the IoT significance and what kind of problems did you have to solve to get there. It's a great pitch and appreciate it if you could get into it. Thank you. Artie, Williams.
Thank you, George. Can everybody hear me?
Yes.
Yes, indeed.
And you see my screen, right?
Right.
Yes.
Okay, great. This is a talk that is essentially a reprise of a talk that I gave to the Long Island Consultants Network. I'd like to say that it's a vertically integrated talk. It goes from the bottom of an oil tank up to a cell tower and then back down again to somebody's eyeballs. So let's dive in and see what's involved here. The order of the talk starts out with the economics of heating oil and why you would want to make a monitor for it, and then how you would design a monitor to measure the actual level in the tank, and how you would then transport that data to the backhaul, which in our case is a cellular backhaul, and then how you present that data to the ultimate user. The ultimate user in POEM's case, POEM, by the way, stands for Point of Entry Monitors. It's an acronym for IoT systems that we make. So the actual end user of the monitor is both the owner of the residential oil tank as well as the oil delivery service. This is not it is not designed to be a retail device, although we did sell some retail devices. And the last part of the presentation is the actual screen that the users see. So there are two types of oil deliveries. One is a contract delivery, where the oil service delivers enough oil so that they ensure that you never run out. That depends on a numerical factor called K factor, which is the number of degree days divided by the historical usage of that tank's oil. If you want to get a little bit more involved in the mathematics of it, it's roughly the inverse of the R factor of your home insulation. Degree days are reference to a 65-degree external temperature. And they're defined as the number of days where the temperature is below 65 degrees Fahrenheit. For an air conditioning system, the degree day is defined as the number of days where the temperature is above 65 degrees Fahrenheit. And that's a cooling degree day. And as I mentioned, it's roughly proportional to the K factor, inversely proportional to the R value of the insulation of your building. And if you you're in the oil delivery service, what does the K factor actually mean to you in terms of gallons that you have to deliver? So it's about 2 milligallons per degree day. So what does a degree day look like? These are from a weather station at Farmingdale Republic Airport. And you can see that it starts out on November 1st, and it goes through the winter, and you can see that the maximum degree day reading is roughly 44 degree days. So you can, of course, use a significant amount of oil during those days. And on June 1st, the degree days drop to 0 because the temperature is above 65 degrees all the way up to September 1st. So the contract supplier has to gauge what's in the residential tank without having a monitor. How do they do that? They use the numerical factor of the 2 milligallons per degree day of heating, and then they know how much they delivered for that tank the last time they delivered, so they know how much the ullage is, which is the unfilled portion of a tank. So that allows them to schedule their deliveries in the most efficient way. That efficiency is usually determined by the delivery service themselves. There are many ways of doing that, but generally they want you to have your tank half full in the wintertime at the minimum. So they use the K factor, but the problem with the K factor is that nowadays you might have, for instance, a heat pump in your house. You might have a space heater of some sort running on electricity, and so that doesn't change the degree days, but it does change the amount of heat that you're going to need inside the building, and that's invisible to the supplier. So these are various, and you may be out of the house, for instance, for a month or so, and your thermostat is set at a low value. But for contract delivery, you cannot have any runouts. If you have a runout, this is a very competitive business. If you have a runout on contract delivery service, generally the residential owner gets pretty angry and they may terminate the contract. And it's a anti-customer retention event. So the second type of oil delivery service is COD supplier monitoring, and that is where the customers monitor their own tank, and then when they need a delivery, they call up the delivery service and they order a certain slug of oil. And what they order is what they can afford to pay at the time. So often these are, since they're cash customers and they're not paying any additional services on the contract. For instance, my contract with my oil delivery services includes free boiler maintenance. COD deliveries do not provide that. All they do is deliver oil. So what does the customer have to do? They have to stick the tank. And this is me at in the basement of the W Hotel in Manhattan on top of a 15,000 gallon tank. About 27 inches there, I think, something like that. Now, if you can't stick the tank, you might have to guess. This is a tank that our monitor is in the lower right-hand corner of the white box. But you see, you can't really get a stick in that tank. It's very difficult. It's a horizontal tank, and then the rafters, the roof rafters of the basement are blocking the ability to get a stick in there. And besides, that vertical distance is only about 2.5 to 3 feet. So you're actually lying down if you want to stick with a tape, as I did in the W Hotel picture. Or you can read the gauge. Most tanks have a Scully gauge on the top, and you can read that. But of course, you have to actually go to the gauge to read it. You have to see it. So the COD supplier is really just going to depend on the residential oil tank owner to schedule their delivery. So if the residential oil tank owner schedules a delivery for 100 gallons, and you're the delivery service, and your truck is out making deliveries, you would rather deliver 200 gallons than 100. So you may put that 100-gallon customer off to the end of the route, or you may actually delay the delivery until you can schedule a truck to come back relatively empty. You like your trucks to go out full and come back empty. What does that mean? These are data points from an accounting company that specializes in home heating oil economics. Their firm is Gray, and Gray, that's the name. So these are delivery statistics for a 275-gallon tank. And out of all the deliveries, you notice that there were almost 3 deliveries of under 100 gallons, that big spike at the 0 to 50 mark. And then there's 1.5 deliveries. The 1.5% of deliveries are to fill up the tank completely, and that's the far right. But the greatest percentage, the maximum number is about 5% of deliveries are between 145 to 150 gallons. But the rule of thumb in this industry is that if you're delivering under 150 gallons, you're not making any money. You're in fact losing money. each delivery each delivery by a delivery service costs between $100 to $150. When we first entered into this industry, we assumed the economics were much lower than that. And at a meeting with our first big customer, the delivery manager, we estimated $35 a delivery. The delivery manager sitting in the back of the room piped up and said, that's way off. It's more like $135 a delivery. So what we didn't account for is truck depreciation, insurance, driver salary, so on. There's a lot of overhead in this business. So as I said, anything less than 150 gallons per delivery loses money. So when your COD customer calls up and says they want 75 gallons of oil, you're going to wait to make sure that that 75 gallons of oil comes out of the last delivery of the day when the truck is almost empty. So how does it actually work? The technician shows up at the tank and they start pumping. The tank has a whistle in it, which is a pipe that is extends down into it's just an empty pipe that extends down into the tank. And as the oil level rises, the surface of the oil plugs the bottom of that little pipe and stops the whistle. The whistle is caused by the escaping air as the tank gets filled. So most contract deliveries make about 6 to 7 deliveries per year. So that's maybe, something like between 1,000 and 5,000 gallons a year. So some of the economics are that the delivery cost, and if you're making 3 deliveries of 145 gallons equals 435 gallons, 2 deliveries of 240 gallons is 480 gallons. If you are able to monitor the tank and you knew what you were about to deliver, you can see that saving a single delivery, going from 3 to 2, saves you a significant amount of money over the number of customers that you might have. As it mentions in the box, a nominal delivery service might have 5,000 tanks. Our first main customer had 17,000 tanks. So so now, of course, you come to the conclusion that you would like to monitor the tank so that maybe you could tell your residential customer, your COD customer, that, oh, you're running low, perhaps you forgot to call. And so what we do with the monitor is that we provide a branded website that the customer can read the monitor on a user interface, and in that user interface, there's the delivery services logo. Because a COD customer can order from anyone, so you want to make sure that they see your logo and know that you're providing the monitoring, so that they can call you for the delivery service. Most of these delivery services, COD delivery services, have rebate programs, and for instance, the rebate program that one of our customers used was that they would charge the customer $200 for the monitor, and then a certain number of gallons delivered over the first year, they'd rebate $100. In the second year, they'd rebate the second 100, and the third year, of course, the monitor was free. Okay, so how did we? Well, we got into this business because somebody at an IEEE event actually came by and asked me about. I thought he was interested in a electrical current monitor that I was making, but he said no, he's interested in tank monitoring. So oil tank monitoring. So I said, why do you want to do that? 1,000 companies must be doing that. And he said, well, he wanted a corporate giveaway, something that they could give away for free to their customers. So we made them a prototype, and we'll go into that a little bit later. The first attempt that we were thinking of was to read the position of the indicator on the Scully gauge, which is that red plastic disc. So we actually made a monitor that did that. We put a magnet on the disc, and we have a series of Hall effect sensors. This is from a patent application. The patent actually was not issued. We did not get the patent granted because Scully themselves has a patent on a similar monitor You see the Hall effect sensors 1, 2, 3, 4, 5, 6, 7, 8, 9. In the Scully patent, they were reed switches activated by the magnet. So the idea was essentially the same. We just made it, modern. 1, 2, 3, 4, 5, 6, 7, 8, 9 are the Hall sensors. 12, item 12 is the magnet. Item 14 is the red indicator. Item 13 is the cylinder called the vial. That's the graduated cylinder is called the vial. And then we have the electronics box, number 10. We have a cellular electronics, number 17, and a power supply, number 16. Oh, I'm sorry, I mistook. It's not a cellular radio for our Hall sensors. It was a Wi-Fi radio. The actual Wi-Fi radio that we use is an AMW0006, which was made by the Zentry Corporation. That's now Sierra Wireless. The actual design of the circuit is here. That's the radio interface that you see there, with some power supply bypassing. And you can see the ADC channels on the left. This is the array of Hall sensors. The Hall sensors can draw 1 or 2 milliamps while they're active. So we actually turn them all off. You can see the U5, 6, 7. These items right here are transistor switches. And the little script that runs on the Wi-Fi radio system on chip device turns the ADCs on and off. And then the power to the ADCs is also turned on and off. And then we have some support circuitry. We had this a bit of memory for the program, and then right, some switch, a high-level switch in order to control the sensor power. The board is fairly small. It's 3 1/8 inches high by 2 and a little bit over a quarter wide. It has printed Wi-Fi antennas, so it eliminates the need for, we're trying to cut costs here. So anything you can do on the printed circuit board without mechanical elements is advantageous. So that's what the device looked like. This is what the customer receives. This is actually a retail device. Our delivery services do not use this device. We installed one for a delivery service because there was no way to install our pressure sensing gauge, which we'll go into in a few minutes. So there's the electronics case, a little bracket that holds the case square against the vial and the magnet. The inset is the magnet assembly that goes onto the shaft. These are some more of the installation instructions. And then the standard connect to your Wi-Fi, the way any other device would connect to your Wi-Fi router. And then the customer gets a little login. That's the Hall effect sensor device. That's the residential retail device. So now when you want to go into something for a delivery service, you don't want something that requires a fair amount of installation effort. You don't want to have a technician go in and unscrew the indicator vial, take off the indicator plastic, replace it with the magnet, screw the vial back on, put the bracket on, slide the eye level into the bracket, and then check that the Wi-Fi is working. That is not at all what a technician in an oil delivery service is trained to do, nor would you want to train them to do that. So how do you make it simple? Basically a turnkey operation for a delivery service. So here are some options. You can measure the pressure of the oil. You can measure the range of the distance from the monitor to the surface of the oil using ultrasound, and you can laser range as well, over about almost 2 meters with an accuracy about 4 to 7%. How would you choose among these? Well, I didn't like the laser or the ultrasonic systems because this is what's called a clean out plug, and this is the bottom of it. This actually goes on the top of the tank. It doesn't touch the oil. But the oil is a bacterial uh, food, basically, and you get a bacterial film and a sludge on almost all the internal surfaces. And I had the feeling that an ultrasonic sensor would be fouled by it, and certainly a laser sensor would be fouled by it. And so I decided not to do that at all. That left us with a pressure sensor. Little aside, this is the actual laser device. This thing probably costs, I don't know, $6. And it's actually a time of flight sensor. And if you think about it a little bit, the speed of light in air is about 1 foot per nanosecond. So if you have centimeter resolution, you're doing timing at picosecond level. This is an integrated device, and it's quite an interesting and very useful device in certain applications. However, we tried it on a PVC pipe, and the inside of the PVC pipe is white, and so we didn't get a good ranging signal, and it was probably due to reflections on the inside of the pipe. That eliminates the laser option because the technician would, of course, have to paint the inside of the pipe with black paint or install a pipe of black iron or something like that. And we weren't assured even that that was going to solve the problem. So what we decided to do is to use a pressure gauge. And we drop a tube into the tank and measure the height of the liquid oil above the bottom of the tube. The pressure gauges are either a Honeywell ABP-M series pressure sensor or a Fujikura sensor that duplicates the Honeywell at 1/3 the price. And they're powered by a 5-volt power supply, but the active range is 4 volts from 0.5 to 4.5 volts, with about a 1.5% error of pressure. The maximum pressure that we measure is 5 psi. That corresponds to 138.4 inches of water. So we could measure 11.5 feet of water. However, oil is lighter than water. The specific gravity of oil ranges from about 0.85 to 0.95. So in fact, we could measure a 15-foot high tank, roughly a 15-foot high tank of oil. So this is the reason why we settled on 5 psi as the pressure sensor. They come in ranges of 1, 2, 5, and then they go up to something like 100. Okay, so now that we have our sensor in place, how are we going to get the data up into the cloud or back to the eyeballs of the user? Wi-Fi is one option. We saw that on the Hall effect sensor device. That was the residential retail device. But it's dependent on the router, and it's got a short range. Router dependency is fairly important because the technician, of course, would have to install the Wi-Fi device, and then they would have to ask the homeowner for the Wi-Fi password. That is a stumbling block and a barrier that the oil delivery companies do not want to jump over. LoRa we considered for a bit, and then I just happened to read something in Newsday when we were first starting this. This is about 8 years ago, that voters in Nassau County didn't like LoRaWAN on their polls. So I said, well, forget it. No, let's not even use it. Let's not even consider it. So we're left now with cellular, but it's expensive. So we that is the one drawback of the cellular option, that it was relatively expensive. So we decided, of course, now to use cellular. So now what do we do about the protocol for delivering the data? We could use standard IoT protocols or MQTT, which is secure, but it has a broker subscriber method. And that really wasn't appropriate for something that is really a device that is sending a data point from its sensor edge, that it's called, to a receiver, a queuing receiver in the cloud. There is no subscriber to this information. It's really just one person looking at one piece of data. So we figured we'd go the browser method, which is secure. However, it does have a high data overhead, and that is the disadvantage of HTTP over MQTT. The number of bytes transmitted per session is quite large for HTTP, but that requires you to look at the data plan that you're going to purchase for your cellular transport. So since we're collecting residential client information, both these protocols are secure, but HTTPS seemed more appropriate since there's no subscriber to any of the data. So the devices that we make are battery operated. We don't want to string extension cords through people's basements in order to turn on the monitors. So how long does the battery last? That's the thing that everybody asks. How long will the battery last? Our initial customer wanted readings every 5 minutes. That customer, of course, ended up, well, it wasn't a customer. That was a potential customer. They wanted readings every 5 minutes. Of course, they decided not to buy any of our monitors, but we were stuck with the firmware that does the reading every 5 minutes. So what does that mean in terms of power demand? So the cellular transmission is about an amp for 10 milliseconds, 2.8, about 2.8 microamp hours. Cellular connection, this is for 1 hour. So you have 12 5-minute periods. 1 hour is 33.3 microamps every hour. The duty cycle, assuming a good connection, might be, 50 milliseconds over 3,600 seconds, and that's one of the advantages of the cellular connection. So how do we get? So now that we know what the power demand is, how many batteries do we need? So this is the Energizer L91 battery. This is the the drum playing bunny battery. The L91 is the typical industrial version of this battery. It's silver. It's fairly expensive, and you can see the advantage of the lithium over the alkaline battery. The alkaline battery would have been, for instance, a copper top. So the L91 nominally has about 3,500 milliamp hour capacity. So how long does the L91 last? So the amount of cellular draw of the current is about 292 milliamp hours, and leaving about 3,200 milliamp hours on the battery. That means while you're not transmitting, you have to provide 366 you have an overhead of 366 microamps. So your circuitry has to draw less than 366 microamps while you're sleeping. So the cellular module that we bought was a hologram dash at the time, and it was advertised to have something like 20 microamps of sleep deep sleep current draw, which was essentially a lie. So we measured it, and it was about 2 milliamps. So that didn't work. So we went to 3 batteries to give us 10,000 milliamp hours. And that gave us a quiescent current of 1.16 milliamps. But still not enough, because the pressure sensor draws several milliamps while it's active. So if you're drawing, even if you're active for just a few milliseconds, it turns out you need at least 2 or 3 milliseconds for the pressure sensor to have a stable output. So you're still drawing those two about 1.6 milliamps while you're taking a measurement. So the only option that was left for us, since we didn't want to go to 4 batteries and then make it just big bulky enclosure, we decided that we would basically turn everything off and reboot every 5 minutes. So this is what we did. The cellular module is here. This is the dash cellular radio with its support circuitry. This is a calendar chip. This is what's in your alarm clock, your $5 alarm clock, soon to be your $25 alarm clock from China. But what happens is every 5 minutes it wakes up and allows the cellular modem to take some data, and it actually stores it in a digest, and then once a day sends that total digest up to the queuing receiving end of the back end software. These are the 2 options for the pressure sensor. This is the Fujikura. This is the Honeywell. This actually, I apologize that this is this needs to be a larger image, but this is what's inside the cellular module. You'll see it in a second. So here is a one processor. This was an open source design which we took over, because when we first got it, it didn't really work very well. So this is a user processor. This allows you to run your own code on the module, the dash. This is the system processor. The reason for these 2 separated functions is that the system processor controls all of the modem commands, the AT commands that drive the whole session. So you don't want your program, which you can do, for instance, in our design, you can program this with an Arduino programming interface. You don't want your user program to screw up the modem and brick it. And that's why the 2 are separated. We have a battery charging and monitoring circuit. The 2 voltage supplies, one for the modem, one for everything else. A battery monitor, and then a level shifter, because these cellular modems run at 1.8 volts uniformly, basically across the industry. The user pins on the device are up here, which we have about 12 digital IOs and a few other pins, resets, and ADCs, and so on. This is what the actual cellular system on a chip looks like. This is what's known as an end-use device, which means that all you do is attach an antenna and you're FCC certified. These are FCC certified on the Verizon network. This is the U-Blox cellular modem. We will talk about U-Blox later. Unfortunately, this is the system processor, and this is the user processor, and we have all the other support circuitry as well around it. There's a SIM card goes in here. You can see we have a little indicator for the direction. USB programmable and battery interface. And the antenna connector is here. So how do you measure the pressure? Now we have electronics all settled. We have the system design roughly in place. So we know what we're sensing, we know how we're sensing it, we know how we're transporting the data, and what actually are we sensing. Normally, if you drop a tube into a tank of liquid, the height of the fluid is basically the pressure in the tube divided by the density of the fluid and the gravitational constant, acceleration of gravity, excuse me. So that's what's shown here. But in order to do that and use that equation, the tube has to be completely filled with air. So in order to do that, you'd have to pump the oil out. Once you insert the tube into the tank, the oil would rise up into the tube a slight bit, so you'd have to pump it out. But we're battery operated, so we can't do that. We can't pump it. Battery would last a day. So that was not an option. So we found this out, by the way, in our initial testing when we didn't do anything. We just dropped a tube into a cylinder of water, and we kept taking readings. And every time the cylinder of water, the water column got very high, the readings would bend over. And we were wondering why it was bending over like that. And I said, wait a second, I can see the water rising up into the tube. And of course, how much it rises, it depends on how deep the oil is. So this seems like a problem that has to be unwound in a certain way. And that actually here is how you unwind it. So as the pressure in the tube goes up with the rising of the fluid into the tube, you can come up with a relationship between the height, which here is a little h, with the height and the pressure, and that's what you want. And the actual depth of the fluid is this equation right here. We decided that it probably would not be a good idea to program this into the user processor in order to figure out what the actual height of the liquid is. So we started taking some measurements. And then we realized that we can get rid of a lot of the deviation in the height by making the volume that the height uses very, very, by making the volume very large, the change in height would be very, very small for a large area. So again, what we're doing is we're compressing a volume. So in order to make the error in the height very small, you make the area of the volume very big. So this is what we did. So you can see here, this is the part that goes into the tank, into the oil. It's basically a plumber's pipe nipple, it's called. Here's a detail of it. It's got a little valve, it's got a little adapter here to adapt to the, we use a plastic fluid, sorry, we use plastic fuel line, which is this length here is 10 feet. Plastic fuel line, it goes to an iron pipe nipple via an adapter. So this pipe nipple provides the area, the large area, compared to the area of the internal diameter of the tube, the pressure sensing tube. So now, when we drop it into the tank, large changes in the fluid level of the tank cause fairly large changes in the volume, but tiny changes in the height. It took a while to figure this out, and I thought maybe that was patentable, but it turns out somebody else has patented 20 years ago to buffer temperature changes in a fluid rather than pressure changes. All right, so now we know what we're measuring, and now we know how to measure it. Now we know what the data looks like, and now we know how to turn the data into a height of liquid. What do we do with it? Well, it gets sent up to an Azure backend, and so this code was written probably 7 or 8 years ago. nobody had IoT code in a general sense, queuing systems and because you have several IoT connections at once coming in, sensor connections at once coming in. How do you choose among them? So Tom Canino, our chief technical officer, with a colleague from Microsoft, developed what's basically sort of the standard um, queuing receiver code for IoT devices. They all roughly look the same way as this. It's all done by a thing here called backend.php. It receives all the data. If the data comes in too fast, it gets throttled back and gets tossed out, and you wait for the next one. The backend then passes it over to the analytic part of the code, which you can see is there are utilities here and the tank size and the tank properties and all this other stuff. All this is now the utility side, and what ends up happening is the display that the user sees, well, sorry, the display that the oil delivery service sees. This is our test site called OilCo. So you get a bar graph with the tank level. The green dot is an indicator. It's a traffic light indicator that tells you the monitor has been working and it last posted an update on November 13th, 2024. These red dots mean that these devices are dead for some reason or other. We don't know why. If you look, Arnie Tankman is me, and these are some battery testing devices. We have the tank properties listed here, and we also had a propane gas monitor as well, which you would have seen on this side. The result is this. So this was the actual tank. I blacked out the name of the user. So you can see that he's got two 275 gallon tanks. They're probably twinned to make a 525. And all right, so here he's using oil in January. He gets a fill. For some reason or other, he's away from the house or something or other. He's using oil in February. He gets a fill. He's using oil in March. He gets a fill. April, he's using oil, but not at the same rate. You can see here how the K factor would be, is how the K factor actually is generated. It's roughly the slope of this curve. The slope gets shallower and shallower as the days get warmer and warmer. And here we're into the summertime, right? And now here, this is November again. What I wanted to point out on this graph is that here's a delivery of about 370 to it's about 200 gallons on a 500-gallon tank. Here's another delivery of about 200 gallons, a third of about 200 gallons. So that's 600 gallons over 3 deliveries. That could have been 2 300-gallon deliveries, and that would have saved the delivery. Here, you don't save anything because these two are, they've learned, I guess. These two are good deliveries, right? You're almost to the bottom. Now you're almost to the top. Almost to the bottom. Now you're almost to the top. So that was actually what our intent was, is to show that you can save deliveries by monitoring tanks. That's the end of the talk. The poem was created by me and Tom Canino, our chief technical officer, and Juan Lopez, who was our chief operating officer. They did a great bang-up job. But I just want to conclude by saying that it's not a money-making business, and we don't do it anymore, and we're not going to be doing tank monitoring. The cellular backhaul and the actual dash modem, which now we call the IOTA, costs about $110 to make. And with the tank monitor fully assembled, that's about almost $200 a pop. And now the prices are probably going to go up a little bit more. And there were some problems with NEMA enclosures, which leaked, and we lost about 10% of our devices. And the final nail in the coffin was that U-Blocks is now leaving the cellular business. So we essentially have nothing to make. So, and that's the end of that. We do sell the IOTA and a second device which replaces the cellular, the U-Blocks modem with a Telet modem. And we have other projects, but we are not in the tank monitoring business because it is a very, very low margin business. And it's very hard to make a monitor that survives all conditions. The last thing I want to mention is that because we do pressure monitoring, we are the only, I think we still are the only company that can monitor a buried tank. A buried tank has two penetrations, one for the vent and one for the fill tube. And the vent acts like the whistle. So there is no way to get any other monitor in there. But we do it by going in with what's called a plumber's T. And the plumber's T looks like the letter T, whereas where the leg of the T is now horizontal. We thread our pressure tube in through the horizontal leg and down into the tube. Now the vertical part of the T is where the fill tube is. So we actually double up on the fill tube with our tank monitor. But that's a very, very small proportion of the tanks. And a lot of companies don't even do underground tanks. They don't even bother to fill them. And the third and final point I want to make is that there are about 9 million oil tanks across the United States, and that number is decreasing. It's not expanding. So that's it's not a business that has a tremendous future, but if you're able to make a monitor for $100 that worked under all environmental conditions, you might do well. But at $200, that price point, the industry doesn't support. So thank you for listening. That's the upshot of the talk.
Really appreciate it. And I think it opened a lot of eyes over here as to what the economics of the oil business is and what it takes to actually go ahead and make one of these things. And thank you very much for showing some of those equations. I think that's a big deal for a lot of us. So thank you. Any questions?
Yeah, I'll take questions if anybody has any.
Does that work for all tanks? Would that work for all tanks, gas tanks, any other kind of tanks?
It does. However, there are environmental requirements on gas tanks that only increase the price. They have to, for gasoline tanks, they have to be explosion proof.
Yeah, so what the IP60s, it's one of those crazy specs. Okay, any other questions from the group?
I just thought of something.
Yeah.
I just was wondering, rather than lowering this thing down into the tank, why couldn't you measure the pressure down at the bottom where it flows out to go into the oil?
Sorry, I can't make out the voice. The audio's a little garbled. What was the question?
I'm sorry, is it better? I was wondering why or whether you could, instead of lowering it down into the tank, if you could just put a fitting on the feed where it flows into the oil burner and measure the pressure there. The math would be a little different because it's moved in liquid, but.
You talking about the feed tube to the actual burner?
Yeah.
Right. Somebody did make a device that measured the flow rate and then tried to calculate the tank level from the amount of oil that actually was being used. There is a device that does that. Again, what happens there is you have the technician installation problem. You know, so the technician's got to come in and cut the feed tube and insert the flow rate monitor. Our device, we advertised our device as, you know, you unscrewed one of the vacant penetrations, the clean out plug. You unscrew the clean out plug, you drop the tube down to the bottom of the tank, you lift it up a little bit so it's the tube is hanging straight down, and then you push a button on the monitor and you leave. Once you push the button, it sends calibration. It sends the first of 5 pressure readings. back up to the website. And then the back office then is able to, well, the technician also does a stick reading. So what they do is the pressure reading then is aligned with the stick reading, and it nails down the calibration of that tank. So it really is just a push button in and leave.
Another question? Oh, another question here. One second.
Just a question on the cellular connect to get data back up to the cloud, Azure. With regard to recurrent charge versus like say a Wi-Fi, you basically it's on the customer, they're paying for the Wi-Fi for their connection to the cloud. Who is paying for this cost for cell connect on recurrent charge? How does that work? Or is there some kind of special arrangement with Verizon that was done? Where you have all these devices and then, you know, some kind of special rate, et cetera. I'm just curious how that works.
Right. So the monthly charges are generally in almost all these monitoring cases. There are other cellular monitor companies as well. They don't do buried tanks, but they also do cellular monitoring. Those monthly charges are paid by the oil delivery service, and then they are passed on to the customer for in the case of COD deliveries, it would be part of the rebate program. That cost will be passed on to the customer. And then after the rebate program ends and the monitor is free, the monthly charges that add up over the course of the year have to be made up by the number of deliveries that you saved. So that excess revenue that you took by making fewer deliveries. In the case of the contract delivery services, that would, of course, would be paid by the oil delivery service, but it would be folded into your contract price. I should mention some details about that as well. I think I don't remember offhand what the cellular charges were, but they are relatively expensive in terms of dollars per megabyte. But our data packet is small, about 2 kilobytes, something like that. So we send up maybe 24 kilobytes a year. And that's what, a thousandth of a second of a movie on Netflix. So our monthly charges for data would be roughly $1, something like that, $1.10 for the SIM card access plus the data charge.
Oh, so yeah, so generally it's rolled into the savings are kind of, you know, so to speak, are rolled into that recurrent charge. But yeah, it was low data. Okay, thank you. Thank you.
Right, you're welcome.
Any other questions here? Fantastic. Arnie, thank you very much. I'm sure.
Thank you, George. Pleasure talking to you guys.
You have a relationship. Thank you. Richie?
Yeah. It's still that.